Hello, everyone. My name is Eren Çelikses. I am a materials engineer in Çelik, and I'm also doing my master in Middle East Technical University on material science and engineering. And today I will talk about the microstructure-based analysis of plasticity and failure of dual-phase steels. So I studied this publication with my co-workers and also with the Middle East Technical University computational solid mechanics laboratory team. So first, this is my outline. I want to start to talk about with my company. Çelik is the biggest galvanized steel producer in Turkey. So, but we don't have in Çelik, we don't have a steel making process. We basically cold roll and anneal the steel. So our income intakes is coil, and our product is coil. I want to mention this because it will be related with my motivation. So I can say dual phase steels are very well known and lots of usage in industry, especially in automotive, since they have high tensile strength and also good elongation and ductility properties. Dual phase microstructure is composed of soft ferrite phase and also hard martensite phase. They are produced via intercritical annealing. So, but the failure mechanism of dual phase steels are kind of complicated since there are two different phases incompatible deformation. So especially there's lots of factors affecting the performance of the dual phase steel, the volume fraction of martensite and also chemical composition of the phases, and also the production techniques are, all of these are affecting the final performance of the final product. Especially some, for example, when you produce your product in not an appropriate way, there will be band structure of martensite. You can see from the paper, publication, the heating rate. If there is a high heating rate, there will be favorable for band microstructure. This is cause there is two different main reasons for this. Mostly segregation of alloying elements during casting, but choosing the inappropriate annealing parameters can also cause this mistake. Actually, this is the thing we suffer in Çelik. There are some problems in our consumers sometimes about the formability operations. So this study is important for us to understand root causes of consumer complaints and also optimization of annealing parameters and also improving the formability of DP800 products. So first we start to characterize DP800 samples. These are two different DP800 samples of ours. As you can see at the left side of the slide, the banded structure of the martensite. At the right side of the slide, the equiax, that's how we name them. So we done tensile test all on these specimens. Actually, the tensile test results are the same as indicated in the standard. We done test in the rolling direction, and yield strengths are and tensile strengths are quite similar, and also elongations are similar. To examine the other properties, we done hole expansion test on these two different DP800 steel. The hole expansion test is basically done via punch. We first open a hole, 10 millimeter hole, then we punch the material. When the outer crack and inside crack reach together, we stop the operation, and in this way we somehow finalize our experiment. As you can see, banded structure has a quite low hole expansion result if we compare with the equaxed one. And also, this is the FLC results of our specimens. There is not quite difference, but you can also see that there is some differences. The P800 still with banded structure as low formability. So to understand the mechanics behind these results, we want to investigate micromechanical modeling. But to do it, first we need an application to convert microstructural images to the finite element model. So our coworker, Mr. Akbaş, designed an application for this, and we call it BORFA. This application basically transforms microstructures into Python code, then finite element model. First, we try with Mr. Kapoor paper, data from the Mr. Kapoor paper, to confirm if this application is working well. So the first trials done with the DP600 steel, actually that works well. So our results can be seen in the left side of the graph. They are quite fitting on the real results, especially with the fine elements. So to do investigation of DP800 steel in Çelik, first we have to calculate the flow curves of the phases. So to do that, we use two different approach. For the Martin side, we use the approach we took from the Perlman's paper. And also for the ferrite, we use the approach indicated in the Layer paper. We calculate the carbon concentration of the Martin side. We are using thermocalc. So we basically give the program our annealing parameters, and we calculate the carbon content of the austenite, and we accept it like it's not changed during solidification, and it remains the same in the Martin side. So these are the data we approach during curve fitting operation. So we done separately for banded structure and equaxed structure. What we done is we fit the model so perfectly for these two cases. And then we done fracture analysis using the flow curve we achieved previously. To achieve fracture analysis, we use element deletion method, and we give some set for ferrite and martensite separately. As you can see from our analysis, at the left side, you can see the banded structure, and at the right side, you can see the equax structure. For the band structure, for both of the experiment, actually, we done uniaxial test, both in the X direction and Y direction. In Y direction means for you in rolling direction. So the band structures are actually elongated through an Y direction. So as you can see from the results, our banded structure actually show an anisotropic behavior. But the equax structure is somehow less anisotropy, shows less anisotropy. So in this study, we done microstructure generation program from an optic micrograph. So we use this mesh, these models to understand the deformation behavior of DP800 steel, and also we use ferrite and martensite parameters. We calculate them for both of them. So compared to equax martensite microstructure, bends lead to premature failure, especially on the bend direction. So our future works, actually, this is just the starting point of our study. We are continuing. We are planning to use this framework in the simulation of hole expansion, and also further computational experimental analysis will be conducted to link microstructure to failure mechanisms.
Thank you very much.